Supercomputer. And we're going to share the screen. Okay, welcome back, everybody. We were discussing, well, I gave you last time homework to speed up implementation of Mandelbrot with F2Pi or PyBint11. Of course, in some sense, this homework has already been done on, well, we already have the solution, but nevertheless, I ask you to try to do it yourself, or at least play with it if you cannot do it yourself. So usually I give 1 week time for finishing the homework. Now, I guess in this case, it doesn't matter so much. It's fine if you send me an email, but I'm not gonna really check this homework very carefully because, well, the solution exists, doesn't it? So somehow it doesn't make that much sense. But nevertheless, I encourage you to try and play with it, okay? You can send me homework if you do it, if you've done it, but it's not essential this time. Next time it's gonna be. Okay, so 1 week. What I wanted to talk to you about today is a little bit about compilation and creating makefiles. I know this is pretty basic. Many of you are probably very familiar with this. So I'm sorry for those of you that might be bored, but I found this almost every year that it's important, at least for some of the audience. So if you're using C++ or C or Fortran or any of those compilers, you need to compile the code before you execute, doesn't it? And the compilation has 2 stages typically. So one is creating a binary, basically the assembler type code or machine code from source files, from sources, which is called compilation. And then the second step is linking, basically putting together these object files, which is objectfiles.o, which are machine code. And of course, during this linking, we also need to add all necessary libraries. There are some libraries which are added by default and we don't even see it, but many of the libraries need to be added ourselves in case we are using some external libraries like linear algebra, BLAS or LAPACK. Now here is a typical example of compilation. So we compile, for example, with the compiler G++, we can add some options here, and then -c, this is crucial, -c specifies the source file. So this means if you have -c, that means that we are compiling. Now I have another similar instruction here in case we had more than one source file. So in most of projects which are slightly bigger, we typically have many source files, not just one, but several, okay? Or maybe hundreds even in big projects. So, and we need to, of course, compile all the source files together, all the source files separately, and then we add all those object files together. So basically, we produce in this step, we produce the output of this step is source1.o. So source1.o is what we get in this step. Yeah, this is hard to see. Source1.o, and then here we get out source2.o. And then we use both source1 and source2 to link together, doesn't it? And the crucial keyword here is -o. So whenever we specify -o, then it means that we are linking, isn't it? And -o means the name of the output file, the executable, name of the output executable. So once more, -c means compilation, -o means linking. However, and then of course, once we have executable, we can execute it like this. Now this dot slash means that we are executing something that's on current directory. Of course, if we have a current directory in our path specified, for example, in the profile, bash profile or profile on your system, then you don't need to prepend this dot slash, isn't it? So then dot slash would not be necessary. Now, many times we have only one source file, especially here in this class. We're going to have small projects, and therefore we might have just one source file. And in this case, we can actually combine together compilation and linking in one step, isn't it? So here, if we have both, if we have just one source file, then you can immediately write -o, okay, executable, and that means that we are actually just producing executable. And here, instead of the .o file, we specify the source file. In this case, the compiler will know that it needs to do two things. It needs to compile and produce executable. So it does combining and linking together, and then of course we can execute. Now, in terms of the options, here I always write options in those brackets. So options can be, well, typical options are -o, which means some minor optimization. It can be -03, which means very aggressive optimization. It turns out that there are typically, you have -01, you have -02, and -03. So there are several levels of optimization. I mean, very seldom you need to tune between -0, which is -00 actually, to -03, because if your code works and it does not, well, if your code works and and you want really efficient code, then -03 is the best thing to do. Okay, maximum optimization. There are very, very, very rare cases where -03 fails. Either it gives you an error, or it actually your code will malfunction. It can happen, but you see this once in blue moon. Okay, it's very rare. And in this case, you might consider downgrading to -02 and see if this kind of bug disappears. So it shouldn't happen, but it can.
Professor? I'm getting errors every time I try to do anything -0 something. Granted, I'm doing this on Windows compilers, but yeah, I'm not able to run that as an option at all.
I see. But this is a Windows compiler inside Cygwin?
Yes. If I omit it, I'm able to run, but I'm able to compile. But if I leave it in there, I start getting error messages.
That is extremely strange. So is it -O? You tried -O.
Possibly. I may have confused the O.
-O3. Does it work? Sure.
I can try it. If it doesn't work, I'll let you know. But in the meantime, please continue.
Yeah, I'm gonna use it here, for example. Yeah, -O is a very standard standard option. Should work. Now, in addition to optimization, we can also use something which is called -small g. Small g means add debugging information. So basically, -g will slow down your code, but it will add to the code also the so-called line information. So information on how is the executable related to your original source code, so that in case you want later to debug and figure out where the problem is, this would have information for you. Now, in addition to this, there is -p and -pg option usually available, which has to do with profiling. So basically figuring out where in your code most of the time is spent. These are useful type of tools, profilers and debuggers, which we are not going to discuss a lot or at all, but you can find information on the web, and I also have some lecture notes from previous years on this issue. Now, the executable, the compiler might be G++ for C++ code. It might be GCC for C code. So C code usually uses GCC. For Fortran, we are using gfortran. It could also be iFort for Intel compiler if you have, let's say, on your supercomputer Intel compiler installed. These are typical compilers that are commonly used. Of course, these are not the only ones. There are many others. Okay, so this is about compilers. We're going to return back to this once we discuss makefiles. But I want to contrast this with what we do with Python. I mean, probably you know this already, but if you don't, I will either refresh your memory or will tell you something new. So Python, of course, is interpreter, and therefore there is no compilation step, isn't it? So you can always, if you have a script, you can always execute it with writing this Python and script name. That's what we were doing from the very beginning. But sometimes this is kind of annoying because you always need to search for this. Well, you always do prepend Python, and many times you would rather have a script which is executable itself, isn't it? So what do we do with Python script to make it executable so that it looks just like an exe file on Windows, for example? Okay, so the procedure is very simple. We have to do two steps. Okay, so one has to do with just changing the way the file is recognized by your system. Okay, so every file on your system is either executable or it's not. For example, manp.py, when I started developing Python code, this was just a text file. So it looked like this, a-x manp.py. So before, when I started to develop things, manp.py, okay, you see, looks like this, okay, manp.py, you see it's not red, okay. Why is not red? Because if you look at permission, so here is this code for permissions, and it tells you that this particular file is readable, but it's not executable. So whenever you have an X here, that means it's executable. If you don't have an X, means it's not executable. You can't execute it. So for example, if I try to do manp.py, the system has no clue what this is. It's permission denied. Okay, you can't execute it. But if I add this execute, if I tell the system that this is executable, then it will try to execute. Okay, so now it turns out that there are three lines here. So first, I think this one means for all. The second three ones means for the group, and this one, the last one, means for me. Okay, so what does it tell me? It means that I can read, I can write, but I cannot execute. Okay. It means that my group can read, it cannot write, and it cannot execute. And everybody else can read, but it cannot write and it cannot execute. Okay, this is what these three sets of three permissions mean. Okay, now this is not executable. So what I can do now is I can change mode. Chmod means change mode, and I can say a plus x and then manp.py. So what does this mean? A plus x. A means that I'm going to change mode for everybody. A means everybody, means for me, for group, and for everybody else. Okay, so basically all three of those flags will change. So flag here will become x, flag here will become x, and here will become x. That's kind of most common things. If it's executable, it's executable for all. It doesn't make sense to change only for myself. Of course, I could tune this and I could change permissions in any way, like only I can execute and nobody else can, for example. Okay, so but if I do this a plus x, it means that I'm adding executable privilege for all. And if I look at it now once more, you see that manp.py changed so that it's now red, which means that it's executable. And you have x here, you have three x's, x here, have x here, and you have x here. Okay, so finally I told the system that this is executable, and this could almost work, but not quite. Basically, there is one more line that you have to make sure it's in your file. Namely, the very first line of the Python script needs to start with this particular line. Okay, has to be this line, which is that you use usr-bin environment. It's basically a command that that searches for proper Python executable and and finds it. Basically, this line normally should contain the symbol, these two symbols here, which means comment and well, this mark, and then it should be the place of Python executable. But instead of place of Python executable, which might be God knows where, somewhere in Anaconda something, you can also use this thing which is called usr-bin environment. Okay, if you use this usr-bin environment, it will automatically find proper Python Python executable. So I can now check if my file has this. Yes, indeed, I put here usr-bin environment Python on top, doesn't it? So therefore, if the system is executable, I can treat it as a normal executable, and I don't need to prepend Python anymore, isn't it? So we have executable. Now, this is of course something that many of you probably already knew, but still might be useful to reiterate. So with this, we change Python script from text file into an executable, isn't it? Which sometimes is useful. Now, of course, for Python, we don't need, this executed. For Python, we don't need makefiles because Python is an environment which kind of, where one script calls another script or includes the third script and the fourth script, and so somehow there is nothing to compile. Okay, but if we use C and Fortran, then we need to compile, and this compilation sometimes can become pretty tricky or hard because you need several options. You need to find proper libraries, you need to find proper compilers and so on. And it's painful to write this every time you want to compile your code. And almost all the projects that have more than one file will come with something like makefile. Now, this makefile is basically just a list of instructions of how to get executable from your source codes. Okay, it's a convenient way to write makefiles. And there is a big advantage of using makefiles instead of bash scripts, for example. I mean, some codes actually use simple bash scripts to compile, but I think this is not appropriate. And the reason for this is that makefiles have techniques to update only those files which have been changed. Okay, so basically it's a technique that has to do with looking at the timings or the time when the particular file was changed. So for example, let's say we have a very, very large projects with hundreds of source codes to compile. And typically for big projects, it might take many minutes or maybe hours to compile. Okay, because compilation is still a slow process. It needs to optimize lots of things, and compilation can take a lot of time. Now, when you change your code, you want to very quickly check whether your change is good, or whether it works, or whether there's a bug or something. So you want to compile this quickly and execute. makefile allows you to compile only only the file or the piece of the code that you changed. It compiles only one source code, only one source file, and it knows which one needs to recompile, because it looks at a timestamp. It looks at when something was changed, and compiles only the piece that has been changed and links together. So this is usually very, very fast. Okay, but recompiling everything, of course, will take much more time, and we don't need to do it normally. Okay, provided that, of course, makefile is properly set up. Okay, so now let me go a little bit through this syntax in makefile so that you can get familiar. Let's write a simple makefile for our project. So so here I write, it's too good practice to write a makefile for every project. Makefile typically contains information about the default compiler, location of necessary include files, necessary libraries, and so on. So I think I explained this. Now on the web, you have several nice tutorials, and you can look at them if you need some more advanced options. I will go through this pretty briefly and give you basic options or basic idea of how this works. So one thing that I want to emphasize first is that the makefile can have only two different names, either capital M makefile or makefile with everything lowercase. Okay, these are typically two name of the files. Makefile cannot be an arbitrary name file. Cannot be anything. It has to be either capital makefile or small makefile. And is typically located in the same directory as the other source files. I mean, you can also have a hierarchical structure of subdirectories if you want to. That happens many times in big projects. But typically, if you don't have such a big project, then it's just one makefile. Otherwise, you typically have hierarchy of makefiles. For each directory, there's some makefile, and then at the top you have another makefile that calls all other makefiles. Now, typically, user would type make, and this would do something. Would usually means produce your executable with default options. Okay, but in addition to typing make, we typically write make and something like instruction. So typical instruction would be make all or make clean. So make all can be make clean, or it can be, I don't know, some people use make debug and so on. Okay, so many times you wanna have not simple make, but you want to have some options. So most of the time when you write make all means produce every possible executable that can be produced from those source files. Okay, that's what it usually means. Clean, it's also pretty obvious. Make clean usually means remove everything. Okay, remove all the executables or the object files and start compiling from fresh. Now, why is this important? Is because if you transfer your source file from one computer to another, so you do SCP, you copy from one computer to another, you have to do make clean, because object machine code on one computer will not be running on different computer. Okay, most of the time it doesn't run. So you have to clean everything first and then compile from scratch. Because if you don't clean, then make will try to only update the new part of the executables or the new things, and that will not work. Okay, there's going to be errors. So make clean is very useful. Then, of course, there could be other options which are up to the user, but these two are much more most common in most projects. Now, of course, you could rename them into anything else, but these all and clean are very common. I mean, this is what most of the projects use. Okay, now how are makefiles written? At the end of the day, everything has to be written somehow by a user. Makefiles are basically just consist of several so-called dependency rules. So dependency rule. Okay, so what is dependency rule? Well, dependency rule means that it has this the symbol here, and you have then on the left-hand side, you have target, and on the right-hand side, you have prerequisite. Okay, so that's the typical dependency rule. And the fact that this is dependency rule comes from this double dot here. Okay, now what does it mean, target? Target means a file or an object, typically means a file, that we want to obtain. And prerequisite means the files that we need in order to obtain that. Okay, now why do we want to specify both? Because the makefile will look at the timestamp at which these two files were last changed or last modified. Okay, so I mean, it should be quite obvious. Basically, if your target is newer than the prerequisite, then should we do something or not? If target is newer, means that we don't need to do anything, doesn't it? Because prerequisite hasn't been changed, so it means there's nothing to do, okay? But if target is older than prerequisite, because let's say that I change the source file, if I change the source file, then I want the target to be updated, doesn't it? So therefore, if it turns out that prerequisite is newer than the target, then makefile will do something. So once more, what makefile does in such a rule, it looks at the dependency rule and figures out whether the left-hand side or the right-hand side is newer, looks at both. And then from that information, it decides whether it will execute the rule, the command or not. So below the dependency rule, there can be, and most of the time it is, so-called command rule, okay? Command rule means real command that will be executed in case the target is older than prerequisite. Okay, so if target is older than prerequisite, command will be executed. That's all there is to it. Okay, once you understand that, you understand makefiles. Okay. Now the command itself is just the regular compilation command that we have to do it by hand normally. Okay, so what is then the advantage of this? Well, the advantage is that this will be executed only when necessary. Okay, of course, if you have just one file, that doesn't look that important, but when you have a lot of files and you have basically a complicated a recipe of how this executable is obtained, then such a makefile is actually very useful. Now, how do you distinguish between commands and the dependency rule? Well, two things. One is that in dependency rule, we have this double dot. And the second one, which is crucial, is that every command has to start here with a tab character. It has to be tab. It's not good enough if it has space. Okay, space will not work. It needs to be tab. That's very important when you copy makefiles, and if you kind of copy it with copy and paste, tab is many times replaced by spaces, and then the whole thing doesn't work. So you have to make sure that that you make sure that there are tabs there. Okay, so the dependency rule defines under what conditions is a given file needed to be recompiled and how to compile it. So what does it mean under what conditions? It means that the target will be obtained from prerequisite. So man_c will be obtained from man_c.cc. In this case, only one file. I could have many prerequisites. It doesn't need to be just one. I can have 10 or I can have hundreds, okay? Many of them. And that means that I will need all this 10 or 100 of prerequisites in order to produce the target. Target is only one, always. Target has to be unique. But prerequisites might be many, okay? The bar rule states that the executable man_c, which is the target, has to be recompiled whenever man_c.cc prerequisite is modified. Now, so if this prerequisite is newer than the target, then we want this rule to be executed. So the rule tells that man c can be obtained by this particular command, isn't it? G++ minus 1 man c and so on, which is called sometimes the recipe. Okay, now we can have multiple rules which are executed recursively. Okay, so typically you don't have just one rule, you might have hundreds of rules. And it turns out that you can have completely independent rule. So typically one rule is for all, one rule is for clean, one rule is for debug, one rule is for one executable, the other rule is for another executable. So you can have several rules, of course, but they will try to get, I mean, the makefile will try to execute them recursively. And you will see in a minute what this recursively means, okay? The point is that makefile has this ability to do things recursively if necessary, okay? We will see this in a second, what exactly does it mean. Yeah, so by default, make will always execute the first rule in the makefile. So you look at the makefile, you look at the rules, and well, there's a first rule always, okay? And the makefile, if you don't give any argument to make, if you don't write make clean or make debug or make all, then by default, makefile will just execute first rule and nothing else. It will not go through all the rules, just the first rule, okay? Now the first rule might call other rules, and therefore it will go recursively. We will see how this works. So the other rules are executed if they are called by some other rule. So basically, starting from the first rule, you might call other rules, and then things will go recursively. The exception is the case when we give an argument to make command, make will start the rule with such a name. Okay, so an argument such as make clean means don't do the first rule, do the rule which has name clean. Okay, so argument means don't use the first rule, use something else. That's all. Now, example of a makefile. Everything is going to become much more clear when we have an example. So we already had this Mandelbrot that is being solved by the C and Fortran compiler. So if you want to produce both the C version and the Fortran version, okay, you can have the first rule here on top, which we're going to call the first rule being all. So if you write make all, this first line is going to be executed. But if you omit all, or you don't write anything, just write make, the first rule will be executed anyway, okay? So this all. Now, what's going to happen? Well, if I write a rule all, it's actually very important not to have a file with the name all, okay? All is not a file. I don't want to have a file that's named all. So if the file all does not exist, then makefile says, okay, all is extremely old. So if the file does not exist in makefile, it means file is extremely old, okay? So what does it mean? It means that this will always be evaluated, okay? So all will always go to this right-hand side and will try to evaluate man C and man F, okay? So the system will look at them, will say, oh, okay, I need to obtain man C and man F. And once I have man C and man F, then I can execute all, which basically doesn't do anything. You see, there is no command below. If there is no command, it means it will not do anything. The only thing that we need is man C and man F. Once we have man C and man F, we are done, okay? Because there's no command. Yeah, now the question is, well, how do we obtain man C and man F? Well, there is a rule. Man C is a rule, and it specifies how to obtain that file. And man F is another rule. So when we write all is equal to man C, needs man C and man F, it means that we will go recursively through the makefile and we'll search for man C and we'll search for man F. Okay, so basically this connects man C with this rule, and this connects man F with this rule. Okay, so then what's going to happen next? Well, we have only one level in this case, but we could have several levels of recursion. In this case, we have only one level, so it's very easy. It says the following. Okay, we need to look at the man C, which is the target now, and we need to ask ourselves, how do we obtain man C? Well, manc can be obtained from manc.cc, which is the prerequisite. Okay, so it's a rule. And in case the executable or the target is older than the source file, then we need to issue this command to obtain it. Okay, and of course this is the command that will produce the executable manc. Okay, and if it turns out, however, that executable is newer than the prerequisite, then nothing's going to happen. Nothing. This manc is done. Okay, so and then we will go to manf, and we'll look at manf and we'll see, okay, manf here, does it exist? Well, fine. It's not good enough. It exists. I need to check the timestamps. I need to check whether manf is newer or older than manf90. If it turns out manf is older than manf90, then I need to issue this command. Okay, and once this command is issued, then I have both manc and manf. I can get all, but then there is no nothing else happens. Once I have manc and manf, I'm done. Okay, because there is nothing in the command for or. Okay, that's roughly how the makefiles work. And you can understand now I could make several levels of rules, not just one step in recursion. I could have 5 or 10 steps in recursion if I wanted to, in more complicated case. Okay. Any question about that? Yes.
So it does. So you said it will not create a file, physical file called all, right?
Will not create. No.
Yes.
Why not? Because we don't have a command here. If we had a command here, then we might create it. I mean, we might. Normally, we would create.
Whenever we execute the make file, how is it going to know if it should be executing all, if it should be executing that rule at all?
No, it will. It will. I mean, what will it will try to execute? Well, it will come to this rule and we will say, well, before I execute all, before I execute anything, I need to obtain manc and manf. Okay, so therefore it goes down to do manc first, and at the time executes this. Then it says, okay, I also need manf, goes down and execute this. Okay, and then it comes back and it says, okay, now I have manc and manf. What do I need to do now? Okay, and then, well, there is nothing here, so nothing to be done. I'm done. And all will never be created. And that's what we need. We don't want to create all, because if the file all was existing, then this all might not be executed and nothing's going to happen. So we don't want to have a file all. All is just a trick to execute several rules. Okay. So let's check a make file like this. I think we have in our computer languages, we have a make file just like that. So we have all, which is manc manf. We have manc, which does something. We have manf that does something, and we have also the clean rule. We use this several times. So if we execute make clean first, it removes all the object. It removes manc and manf. Now it doesn't exist, doesn't it? Manc doesn't exist. Manf doesn't exist. So it was removed. Then we write make. And you see that the first execution, the compilation of manc.cc has occurred. Then compilation of manf f90 has occurred, and that's it, finished. Okay, that's exactly what we expect, doesn't it? So this will need to, it will start evaluating all, and it will first do the first rule, which means this. Then it will do the second rule, which means that, and then it stops. It doesn't do the clean. Okay. So what if I do make clean? Then it executes only this last rule, make clean. Okay. Clear. Once more, make does the same thing. But if I type make again, it says nothing to be done for all. You understand why? Because it checks the timestamps and it sees that, well, no need to do anything. This works almost always, except that you know, the timestamp is exact up to a second. Okay, so you see the file make file has been changed. Well, these executables have been produced at 1740 and source file 1726. So if it turns out that the source code and the executable were kind of done at the same second, then makefile could malfunction. But I mean, this almost never happens. Humans are not so fast, isn't it? Second is for us quite a lot. So if you change the source code, it typically takes more than a second, and that usually is fine. So the makefiles work pretty well. Looking at the timestamp is pretty efficient. Now, oops. Hoppala. My iPad seems to have an issue. Oops. Okay, it's back. My iPad froze for a little bit. Never happened before. Okay, so we understand this. Now, what else can makefile contain? Well, typically we want to separate the compilers or the name of the compilers and the rules somehow. Why? Because typically we use the same makefile or slightly modified makefiles on many different computers, and computers typically have slightly different compilers, or we want to check different compilers out, or when we port to another computer, we are forced to change the compiler. So therefore, it's a good idea to specify certain variables which contain name of the compilers. Okay, so for example, G++ is the name of our compiler, and G Fortran is the name of our compiler, and we want to set a variable. In this case, I'm going to call it C++ and Fort as to remember, which is going to be used then in all the places in a makefile. Okay, there could be many places where this is going to be used. And then typical things that we also specify is so-called C flags, which is the so-called options or flags that you're going to give to a C compiler. And then then usually we use something that's called F flags, which means options that we are going to give to Fortran compiler. And for example, options could be -03, which is the maximum possible optimization. We could also have -G if we want to debug things, or some other option, depending on the system. So we usually put this in the very top on the makefile, like a header, isn't it? These are the options that might be different on different computer. Okay, and then the rest of the makefile is something that user should never touch. This should be done by developer. Okay, user might need to change this compilers on the top. That's how we usually think of makefiles. That this compilers on the top might be system dependent. So when you get a new source code from somebody, you might need to tweak this. But everything below this, okay, here, this part should be something that is that should be done properly in such a way that it should work on every computer. Okay, so now the rules here, of course, are exactly the same as before, except that here we are going to use variables $C++ and $C flags. Now you see that the makefile is a bit different than Python or any other language, in the sense that if you have a variable, when you define the variable, you don't use a $sign or anything in front of the variable. You just use any symbol, any string, and you define the variable. But when you use the variable, you need to prepend this dollar and brackets. Okay, so you need to put it inside this strange dollar bracket sign. Okay, when you use the variable. So in other words, using the variable needs a different symbol than specifying the variable. Okay, it's a particular thing for makefiles. That's how it needs to be. Okay, so we define on the top various variables, and then here we use those variables instead of typing the particular type of rule that you need to compile. Again, the reason that we are doing this is because we want the makefile to be as general as possible, so that you don't need to tweak it when you move from computer to computer. Okay, so yeah, we have done this here as well. So if you look at the makefile again, you see that my makefile indeed, whoops, makefile, yeah. This makefile indeed contains variable on the top. In this case, I call it CC rather than C++. So there are a couple of variables which are kind of common. CC usually stands for C++, or C++, it stands for C++. This is standard. Just one C, like capital C, usually stands for C compiler. F90 or Fort usually stands for Fortran compiler. I mean, you can come up with any variable you want, but these are kind of standard. Most people use it, or they're common. Now it turns out that you can specify, if you don't specify those variables, let's say that I didn't specify, this is a comment. So if I didn't specify CC in here, okay, and I still wanna run. Look, it's interesting. This thing does try to compile something. Okay, so you see, I didn't specify what variable CC is. I comment out. Okay, I didn't specify, but when I compile this, actually this thing tries to compile it with something. I mean, it tries to compile it with CC, and there is an issue because CC doesn't exist. But nevertheless, actually it does exist, but it's a C compiler of C-lang type, so it doesn't have fopenmp. Now, what do you think? How does system determine where to get information about CC if I don't specify it? Do you have any idea? So again, I'm using this variable .cc and I'm not specifying it. The system still tries to do something. Any idea? Well, it turns out that if makefile doesn't specify certain variable, but it uses it, then the system tries to find environmental variable with the same name. Okay, so if I do this, if I just change my environmental variable to G++, I think then it should work. You see, now it tries to use G++. It works. Okay, so similar, F90, for example, is not specified here, so it doesn't find it. Now I can do export F90 is equal to G Fortran, and I see. So this doesn't work because I need to use compiler which has openmp, so G++ -10 in my computer. Okay, so you see, if I specify environmental variables instead of specifying them inside makefile, the system will, the compiler will also work. So that's one way. So one way is to not specifying the compilers and doing this through environmental variables, but probably it's a better idea to specify them on the top. I mean, both are valid, and different makefiles, different people do it differently, but I prefer to specify the compilers for your platform, and then when you port, you just change that top header file. Okay, so we understood this part. Any question? Any question up to now? Is it so clear or it's so boring? Neither.
It's clear.
Okay. Clear. Okay. Thanks. Okay. So as I discussed before, we typically have more rules, not just one, because we sometimes want to do other things like cleaning, or we might to produce a debug version of something. Then might be another rule. But clean is typical. So clean, if you don't specify source, so what is this called? This is not target, but prerequisite. Yes. So if prerequisite on this side is not specified, if it's not specified, it means that the rule will always be executed whenever you invoke it. So of course, whenever I say make clean, I don't want the timestamps to be checked. I want the thing to be cleaned. Okay. So if it's nothing on the right-hand side, that means this rule will always be executed. And so then it says, well, no matter what, you have to execute what? Well, you have to execute the command to remove -f, -c, -f. So what does it actually do? Well, it removes these two files, and this -f option here means remove use force to remove, okay? Force, which means that don't complain when such files don't exist, okay? So typically when you write to remove -c, -f on some systems, it might ask you, are you sure you want to remove, okay? And of course, when you use this in Makefile, we don't want to be asked, okay? We want things to get removed, no questions asked. That's one reason why we ask -f. And the other reason is that sometimes these files might not exist, and then we will get an error. And we also don't want to see errors, okay? So -f means force, shut up, don't tell me there is an issue, okay? So this will always get executed and without complaints. Yeah, dependency is empty, therefore this is always invoked. To invoke the clean rule, we need to use make clean. Yeah, we already discussed this, that in order to invoke a rule, which is not the first one in the make file, you need to give an argument, which is name of the rule, make clean. Okay, so last time we already mentioned the special variables. So it turns out that Makefile tries to be a little bit user-friendly, or tries to make our life slightly easier, although less readable sometimes, and provides several special variables such as $at, $less, $star, and there are many others. Okay, these special variables mean something. Let's walk through. So the variable $at stands for the target on the left-hand side. Okay, then the $less, for example, stands for first item in the prerequisite list. And I don't remember what is $star. So let me demonstrate how do you use this. Well, again, let's say that we have this rule here. man_c is obtained from man_c.cc. And then when we actually specify the command with which we want to compile this, it's kind of boring to write the same thing twice, because here we would need to write again man_c, and here we would need to again write man_c.cc. Okay, you repeat the same information twice somehow. Okay, and we're kind of lazy to do that. Therefore, Makefile or make allows us to use the special symbols, which means $at is equivalent to what was on the left-hand side of the rule, and $less is what has been on the right-hand side of the rule, but the first item. So if there are more, it always takes the first item. Okay, and now you see that if you use these rules, you can do the same with manf. Then you see that all those rules then become the same. You see this rule for compiling C code and the rule for compiling F code look almost identical, well, except C flags and F flags, but otherwise they look identical because the symbol is identical, the symbol is identical, so they look identical. Okay, so that's nice. But the point that many rules look identical, we can exploit that, because when things repeat, we don't want to write the same information many times, isn't it? So there is something that's provided in the make files, which is called default rules or pattern rules. Okay, pattern rules. So instead of writing every time the same thing, we might just write a pattern, and then the pattern will be executed whenever such a compilation is necessary. So this is the last thing that I want to discuss here, which is pattern rules. So what typically these pattern rules mean? Well, you see, when we have many C++ and Fortran files, like, or many things to execute, or no, to compile, which need to be compiled in a similar way, we can define generic rules. So we're going to discuss generic rule. For example, we can define a rule that produces .o file from corresponding .f90 file, or we can or .o from .cc file. Okay, so we might say, well, as soon as we have a .cc file, the makefile will specify the rule how to obtain .o file, which is the machine code, doesn't it? Linking, of course, is not generic. Linking depends for every executable, is usually slightly different. But compilation is usually pretty generic, and you can specify a rule for that. Okay, so here is the typical pattern rule. So this means that we can produce .o any, this percent here means anything. Okay, any file that ends with .o can be obtained from the same name .cc. Okay, so let's say you have a .cc file, then this rule can produce from .cc the same file with name .o. Okay, that's what this pattern means. And here is the command, how to do that. Okay, the command is, well, as we'd expect, invoking the C++ compiler with -c, and then there is $less, and this $less, as we discussed, means take something from the right-hand side, so which is the name of the source file. Okay, quite obvious. Now, in the same way, we can specify the rule that if the file name, there is a file name .f90 exists, then we can produce the same file .o with this rule, which is slightly different, but a rule for Fortran files. Okay, so we have, for example, these two rules, and from now on, we never need to explicitly invoke C++ or Fortran compiler to produce object files. Okay, this is generic, works always. Okay, so it's useful sometimes. Now, there is one thing that you have to be careful about when you write these rules. Well, in general, in making makefiles, in compiling or having makefiles, is that what happens if you have a file with identical name but different ending? So let's say you have mont.cc, but you also have mont.f90. So what's going to happen? Well, if you have that, that's a problem. The system will be confused. I mean, it's either going to execute the first rule or the second rule, but it will not know what to do, because the system expects you to have unique names. So because of these rules, you should not use the same name for two different source files. Okay, I mean, it shouldn't happen anyway. You shouldn't be sloppy. This is, if you're sloppy, then you might give exactly the same name, and then makefile could malfunction. Okay, so because you have rules and you don't know which rule to execute if you have this two files with the same name. So be careful, don't do that.
Sir?
Yep.
Why, with these ones, we have $C++, $C flags, and then go right to -C, whereas in all the ones beforehand, we had -O.
Ah, okay. So -C here is for compiling. Okay. And -O is to produce, is basically for linking. Or -O can also stand for compile plus link. Okay, so when you have only one file, then we typically do compile and link together, and therefore we use -o if you have only one file. And also, if you just link together at the very end, we also use -o because that's the linking command. But here we are doing compiling separately from linking. Okay, so why do I do that? Well, because the usual story is that linking is not generic. Linking is very rarely generic. Compiling is generic, but linking needs different object files, and you need to specify which object files are.
Does the linking come later then in this case?
Yes, absolutely. So the way it works is that first you compile and then you link. Link is the last step. We will have an example like that in a second. Ah, no, we don't have it here, but I prepared for you something. Okay, so yeah, I wanted to show you here. Try. In a try, I prepared slightly different make file, similar but slightly different. But first, let me show you how this might be useful. So I use our code monthc.cc to split it into two codes, okay, into two different pieces. So the first piece is very, very simple, and it contains only the subroutine, this function, month.lb function, nothing else, okay? We can always do that. We can put this in separate file, and then monthc2.cc contains everything else. So here I commented out this function because it appears in the other file. Okay, and what I have to do then in order to compile this, I need to use definition. I still need definition. I need to say that this particular function exists. This is definition, but you see, it's not implemented because I have here semicolon here. Semicolon means immediately after the definition, semicolon, no implementation, means such function exists, but it's not being implemented. Somewhere else in the code, somewhere else in some other object file will be implemented. Okay. Of course, in general, you can have many of those. Imagine that you have hundreds of them and many other files. Then what do? Well, now I have two C files, and I need to produce an executable out of those two C files. Okay. Now I cannot avoid linking, okay? Because I need to produce object file from the first month c1.cc. I need to produce object file. I need to produce object file from month c2.cc, and then I need to link them together, okay? So therefore the linking is important when you have multiple files. And that's quite common because big projects means you want to have multiple files. You don't want to have one file that has 100,000 lines, doesn't it? You want to logically split the code in some sense, okay? Now, how does the Mig file then looks like in this case? Well, let us look at it. So I'm gonna, of course, I can have all, which means that I'll need to produce month C and month F. Month F is just like before because I didn't split it, but month C is now changed. In particular, month C will be obtained from month C1.o and month C2.o. So from two object files, not from the source files, but from the object files, because I need object files. And and here it's the linking command, only linking, not compiling. So we will create it from with C++ compiler, which has -o option, which means linking only. And of course, the output file will be on month C, which is the left-hand side of the rule. And in order to do that, we need the two object files. Okay. Now, in this case, I cannot use the variable .less because .less will take only the first item on the right-hand side, not both. Okay, so I need to actually specify them. Now, you see that I don't have a rule how to obtain month C1.o or month C2.o. Okay, I didn't specify here. I could have, but I didn't. Okay, so what's going to happen? Any idea? what's going to happen? So the compiler will come here to mand C, and then it will say, okay, mand C can be obtained with mand C1.0, mand C2.0, okay? But those two, let's say they don't exist. So what's going to happen?
So you're going to go down to those bottom two lines?
Yes, it will go down to this. Well, first it will try to find the rule. And if the rule is existing, then of course it will execute the rule. But if the rule doesn't exist, then it will go to this line and will say, oh, okay, I know. I have this pattern. So I can obtain the O file from CC file. And it will look whether such a CC file exists. And then it will execute this. Well, if CC file doesn't exist, maybe F90 file exists, okay? And we will look for this rule. So it will need to try to find the rule with which it can obtain that. If it doesn't find the rule, then it will boil out and will say, I don't know how to do it, okay? But if the rule exists, then it will work. Okay, so let's try. I don't have an object file nor executable. I type make, and you see, it immediately figures out how to this produce an object file. Okay, that's the first object file. Then this one creates another object file, .o, and then it links together the two. Okay, so in this line, we use the first pattern. In this line, we use the pattern again. And then here we have the linking. And then the fortran has been executed in the usual way that was done before. So now you see that we have all object files. We have one object file, we have another object file, and we have the executable. Okay, now if I do make clean, I remove, of course, all of them. And I do make again, and I produce first the two object files. Then I produce the executable from the object files. And finally, I should probably increase this a little bit. And then finally, I produce also the fortran in the same way. Okay?
Professor?
Yes?
Just want to make sure I'm reading this right. So when you did make, you actually came up with two executable files, right?
Yeah, so basically this one produces mand F executable, and this line produces mand C executable, doesn't it? Because this one has -O mand C, and this has a -O mand F. So this is the linking step that produces executable, and this is the linking step that produces executable. This one is just compiling, and these two are just compiling.
So if I understand this correctly, then you didn't do anything to link the two executables together.
No, because there are different executables. They don't mix together. No.
Okay, thank you.
Okay, I have two executables, isn't it? Mand C and mand F that are completely independent, have nothing to do with each other. Okay, so anything else? No, I didn't have anything else to say about that. So with this, I'm done with introducing makefiles. So I hope that there's at least a little bit more clear what makefiles do and how they're supposed to be written. So if you need more details, of course, you can read lots of online materials about this, lots of tutorials on makefiles, which were specified here at the beginning. But I mean, for this class and for most of the projects that you might encounter, this short introduction might be already sufficient, in my opinion, for using makefiles from now on. Okay, any question?
Hi, Professor.
Yes.
So can you show us how you split the same source file into two files?
Sorry, how I split or what?
Two source file, like so how you split one source file into two files?
Yeah, how? I mean,
yeah.
The first approximation, it's completely up to your will. I mean, you can do it in any way you want. Of course, there are some issues. I mean, sometimes there are certain ways you cannot split. Okay, it depends on dependency. Okay, so for example, mandc1.cc, no, mandc2.cc. So if I have just a normal function, okay, normal function, then I can always specify it in its own file. And basically, many people encourage the source code to be in such a written in such a way that every function has its own file. I mean, sometimes if it has small functions, you don't need a separate file. But a good practice is that most of functions should be in their own file. And then when you need them, you see this mandel b is needed down there. You can call it just like before. Okay, so the source code is identical to before. The only difference is that I had to specify the definition, only the definition for the source code. That's all. So the only modification from before is that I copy paste the function, just put it somewhere else, and then I had to repeat the definition, because if I don't repeat the definition, for example, this is now commented out, I didn't repeat the definition, and I tried to compile, it will say, mandel b was not declaring the scope. Okay, it doesn't exist. When I compile things, mandel b is missing. Okay, so now if I just repeat the definition, then at least the combining part, it will work. Now there is an issue here. The compiler says this function exists, but it's not yet specified, but that's okay. That's what compiler says. Okay, so actually, if we look at the mandc2.c.o, okay, so it turns out that there is a way to look at the at every object file. Remember, this nm is a useful command. Okay, what does it do? Is it lists all symbols which are either defined or undefined in your machine code. Of course, this is hard to read. I mean, there are lots of symbols that God knows where they come. Mandel B, RKST7 complex IDE something. Okay, so the machine does this weird symbols, but you can recognize them. Actually, Mandel B is, of course, our function that is an input, is basically needs a complex number. Okay, so and there is U here. U means it's undefined. It means it's being used, but it's not defined. Okay. Mandel B, yeah, and that's the only place where there are not so many symbols actually here. It's a small thing, but the point is that it says Mandel B is undefined. So if you link and try to produce the executable, and this Mandel B is not defined anywhere, there's going to be an error. Okay, but look, if you look at mandc1.o, you see that this thing, mandel b, now has a T symbol here. T means defined. Okay, so it means that this symbol is defined in this mandc.1o, and then it's okay. Okay, so therefore the linking works. So you can, to a first approximation, you can split the source code in any logical way, in the sense that any function can be in a separate file, or you can compile it any way you want, provided you then write definition. Now, things get a little bit more complicated when you have templates, where again, you need to, whenever you want to use a template, you need to define it. And then the problem is that if you have multiple definitions of templates, they sometimes can collide. I mean, things can get a little bit tricky when you have more advanced things. So, but the first approximation, if you don't go into this definition, complications of objects and templates, you can pretty much cut the code in any way you want.
Okay, thank you.
Okay. Any other question? Too simple, huh? No questions? Okay, if no further questions, then I want to go to a slightly different topic, which has to do with parallelization. So I mentioned several times the importance of parallelization, and I want to emphasize this a bit more. Why do we bother so much with parallelization, and why is this such an important topic? Well, in the past, it wasn't so important. Why? Well, because computers tend to get faster and faster and faster with time, but number of cores that you could have at your disposal was of the order of, I don't know, 10, 100, 1,000. I remember times when 1,000 was a really big number. Okay. But now, if you look at this top 500 list, top 500 list is I think it's updated every month, and it lists the 500 fastest computers in the world. Okay. If you look at this list, you're going to see currently, I think this is still valid, hopefully, currently the fastest supercomputer in the world is in Riken in Japan. It's a Riken Center for Computational Science. Actually, I know this place pretty well. I was there. And it has 7 million cores. 7 million cores, okay, together. That's the reason that's so fast. And the peak, the maximum performance is in teraflops per second. It can do 442 million teraflops, no, 442,000 teraflops, okay? So 1,000 teraflops, so here I have a dictionary, 1,000 teraflops is, I think, petaflops. So it means it has 442 petaflops currently, isn't it? That's the fastest computer currently in the world. Now, of course, this changes. So in a few months from now, you might have, I don't know, thousands of petaflops, which is then exaflop. Now, next one on the list. So US is not the first, and it hasn't been the first for quite some time. Before that, I think the first was actually China. But the second one currently on the list is Summit. This is US, IBM system, which has this, what is it, 3 gigahertz NVIDIA accelerators. Now, I mean, this is nice that we are on the list the second, but unfortunately, you have to be aware that this is mostly because of GPUs. GPUs give a lot of teraflops, but they're not a general purpose machine. So unfortunately, we are not first, and even the second is kind of questionable because of the GPUs, which give you speed, but it doesn't give you general enough instructions. Now, what about the third one? Yeah, the third one is also US. And then finally, the fourth one, I think, is this one in China, which used to be #1 for a long time because it has such a big number of cores, 10 million. Now, why do I discuss this? Because I want to emphasize that the big computers in the world, all big computers in the world, have enormous number of cores, millions. Okay, which means that if you want your code to be runnable on any supercomputer, it has to be massively parallel, not just a little bit, but very parallel. Okay, otherwise you just can't use any of those powers. And this is a general trend. It's not just from this year or last year. It's basically going on for several decades. That the number of cores is just increasing. This is going up exponentially. Okay, and in a few years from now, every little computer center will have thousands of cores, not just a few. So therefore, the important thing is we need to learn at least a little bit how to use this massively parallel resources. Okay. Okay, but before we go into that, I just want to quickly explain you what these numbers mean, this teraflops per second. Okay, so how do you obtain teraflops per second? Well, the way they're supposed to be obtained in this list is these administrators of these computers need to run a certain benchmark. And this benchmark is actually just running those linear algebra problems. You know, the linear algebra that I told you about, Lapak and Blas. Basically, it's some collection of this Lapak and Blas routines that need to be run. And then this is a standard way of checking the speed of the computer. However, you can calculate the speed of the computer, the theoretical performance of the computer, without running anything. Now, of course, this would give you theoretical speed. It will not give you the actual speed. And however, if the Lapak and Blas are compiled reasonably well, you should get close to like 80% of theoretical speed. So in other words, if the computer is really run well, in the sense that libraries were properly installed, you should get to roughly 80% of the speed of the theoretical speed. Now, theoretical speed is very easy to calculate. It has to do here it's specified. It has to do just with clock tick, how fast is your computer, how many gigahertz, and how many cores you have. That's it. Just multiply these numbers together and you get how many flops you're supposed to have with you're supposed to achieve with your computer. So that's sometimes useful because you have at least the feeling of how fast is your computer compared to, let's say, the fastest computers. But we're going to do this math next time because time is 6:20 and we're running out of time. So any question? No? Okay, if there are no questions, I'm gonna stay here for a little while, but you can leave. We're gonna meet next Monday, isn't it? Next Monday. Goodbye.
Thanks, Professor.
Thank you.
Hi, Professor.
Yes.
I just curious about one question. Like,
Yes.
if you have a GPU